Welcome to this paper club, and today we're going to talk about calibration on modern neural networks, which is actually almost the name of the paper. So what is calibration? They start with the definition of calibration. It's a very important definition. The problem of predicting probability estimates representatives of the true correctness likelihood. Why is this important? So I suppose most of you have played with neural networks, and you know that if you have a classification network, the last layer is a softmax layer, which outputs a thing that sums to 1, but it's not a true probability. It can be defined as a probability distribution because it sums to 1, blah, 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 but it does not represent the probability of those things to happen in reality. So you shouldn't mistake it for a probability distribution of your prediction. And this paper is all about how can we make it closer to the actual probability distribution of what the neural network thinks. So we can split this paper in 3 major parts. The first part will talk about what is calibration, how can we measure it. The second part will be what is the impact of several settings of neural networks on the calibration of the final output. And lastly, this paper is about methods to calibrate the neural networks. So let's start. Why is calibration important? So most of neural network tasks want to predict what is the most likely class of something, and you are only concerned with knowing which is the most likely class or which are the most likely classes. But sometimes you want to take the probability of that class being the actual reality, the truth. For instance, imagine that you go fast forward 5 years into the future, you have neural networks at your doctor, and your doctor say, oh yeah, you have like 50% chance of having a deadly disease. That is a very bad news, and you want to make sure that that information is correct, because there will be people using neural networks that do not know that the softmax is not truly representative unless you try to correct it, which is the point of this paper. So at the start, the first figure shows that in 1988, the state-of-the-art for CFAR 100 at this calibration plot, the x-axis is the softmax output, and the y-axis is the true probability for each beam of softmax output. And on the right, you'll have the same thing, the state-of-the-art network, but for 2016 for the ResNet. And what you see is that this network is underconfident. This means that the softmax probability is higher than the real probability. So, sorry, the other way around. Did I say it wrong? I think I said it wrong. This one is underconfident because, yeah, the accuracy is higher than the softmax. I said it the other way around. So this is underconfident. So when you see these type of plots and the things go above the diagonal, it's an underconfident system. And the other way around, the state-of-the-art networks from nowadays are overconfident. So the probabilities that they say they have are actually higher than they should be in reality. And when you see these type of plots with the actual outcome below the diagonal, it's an overconfident system. So if we were able to correct it, we would want these bars to go down and these bars on the right to go up. So the output of the softmax resembles the true probability of that thing happening.
Just this relates a bit to one thing that we were speaking last week as well, which is that even though, so you see the top plot instead of the bottom one, you see that the average activation is also a lot higher, which is why we get that overconfidence. But last week we spoke that some neural networks actually are well calibrated and some are not. And that's what you can see here is that the LENet, which was from 1998, was a lot better calibrated than the ResNet of today. So we were having a bit of an argument last week about that. about, well, but some networks are calibrated, yes, but the thing is that modern networks are terribly overconfident.
Yeah.
Yeah.
And don't think that confidence is the holy grail. I would rather have ResNet than the other one because there's a much higher accuracy. So the ideal scenario would be to keep the accuracy but get a more calibrated output if you want to use the output as a probability distribution. So the second section of the paper, which is still on the first point I described before, is about how can we transform calibration into a scalar so we can compare it, so we can make decisions. So the first way, the first piece of information you need to know is this concept of reliability diagrams, which is this plot, these two plots. And it's pretty much consists of splitting your softmax outputs into beams and then comparing, seeing what is the percentage of a specific beam of actually happening in reality, and then you can produce those plots and visually you can compare. But well, this doesn't tell us the whole story, because if you look at these plots, you have no idea if you have a lot of samples here, or a lot of samples here, or a lot of samples here. So you don't know what is the distribution of softmax output. So ideally, this should be seen with the distribution of samples for each beam. So as you might imagine, if a given beam has way more samples, you probably want to calibrate it more precisely than a beam that has pretty much no samples. And this is what the writers argue when they define this metric, which is the expected calibration error, and it is the main metric they will use throughout the paper. And it's pretty much the L1 distance in those buckets in the previous plots. And if you average those L1 distance weighted by the counts on each beam, you'll get exactly the same metric, even though it is explained in a different way. Another metric that they consider is the maximum calibration error. So in some systems, you are more concerned in not being wrong at all, so you want to penalize the worst case scenario. This is like the infinity norm. So in those scenarios, you might use this metric instead. I mean, you can use any metrics you want. You think that it makes sense. Internally, we are experimenting with the L2 metric, but it's a matter of flavor. The last thing they want to mention is the negative log likelihood, so the cross entropy of the output. They don't use these as much as the final metric of the things they want to compare, but this metric is important to actually calibrate the networks using some of the methods. So it's important to keep this metric in mind. So by now we can go to the second part of the paper, which is for me the most interesting part in terms of insights, which is what happens if we change the parameters of our network with regards to the actual error and the calibration. So they describe pretty lengthily what happens in each of these plots, but I think the plots